So we have two presenters who are going to talk about health disaster offices in St. Vincent, Dr. Luigi Di Sano, which we all know, and Mr. Riyad Rahman. Just give you a short brief on Riyad. Riyad is a structural engineer with over 20 years of experience in structural analysis and design. He previously practiced in London. Without further ado.
Good afternoon.
Afternoon, everyone. Finally, we get to talk about some real structural engineering there. I don't know if anybody's excited. I don't know. We're going to talk about modeling, analysis, and output of a building on base isolators, and how, if is it beneficial, should we be doing this? The building is a 3-story RC building with sloping land with a back level that's lowered for parking, reinforced concrete. As you can see, it's an engineer's dream in terms of grids. 5.35 meters both directions. Sorry, architects and everybody else, but someone once said they care about functionality first. Couldn't agree more. 500 square columns. Okay, RC building. No fancy architecture. No, go ahead. Thank you.
Thank you. He's employing me. That's good.
You're doing a good job. These isolators now, it's a suspended ground floor. The other floors are suspended. The isolators are located under the ground floor, not the traditional slab on grade which we do in the Caribbean, which we'll get into a little more detailed. It was modeled in ETABS, right? And the foundation structure was modeled separately for complexity reasons and a separate behavioral assessment. But we're talking about the superstructure today. Oh, I have this. See, no? Okay, so this is where the isolator is located. This is the ground floor. This is the pedestal, your foundation, and tie beams. So the RC slab is left out here, but the isolators are located at those junctions. Right, performance goals. This is a matrix, performance matrix from the Building Seismic Safety Council in collaboration with NARP in 2009, who decided ASCE 7, well, what is really their performance if you use their prescriptive designs, right? Let's build a matrix of it. So you would think, well, category 4, excellent, occupancy category 4, right? It must be operational if you follow the code. Not so. The expected behavior for occupancy category 4, even, well, for your maximum considered earthquake, is only life safety. Collapse prevention, life safety, plenty damage still, right? So what should we be going for? This is frequent earthquakes, design earthquakes, MC earthquakes, right? Different return periods. We really need to be building an essential facility for something that can perform up to here, operational after a maximum considered event. We think base isolators should be used. Well, Professor Luigi and I think so. But I got some consultation from the chairman of ASCE 716, the godfather of performance design. I thought he was going to tell me go to performance design. What does he say? If it is truly desired to have a hospital that's reliably capable of following either a design or maximum considered earthquake event, we recommend the use of base isolation as a means of controlling damage. So not just Professor Luigi and I are saying this. The godfather himself said it. Right, so let's get into the modeling gymnastics. I am the puppet engineer under Professor Luigi, who knows everything. So I'll just explain what he told me to do. Right? Where you see these springs there, he told me to put the isolators, right? And the red spaces there are friction sliders. Different, no lateral resistance. The rubber isolators have the lateral resistance. However, you had to keep playing around with locations of both of them and interchanging. Why? Because you want to make sure your center of mass and center of rigidity is not off. So you don't get that twisting, with that torsion, etc. So what's the properties of the damper, the isolators in both directions? 550 kilonewton meters we're going to start off with. Now it's important to note that these things are round, so the stiffness is the same all the way, all directions. What that means is if you have a force on an isolator, 550 is going to move 1 meter. Right. So what's our earthquake we're designing for, right? We're designing for SS period of 1.24. That's our short period spectral acceleration. This is what we put it in the computer. You can see a rigid building, one with shear walls or bracing, right, is going to experience the most from the earthquake in terms of spectral forces of the building, which is bad, structure and contents-wise. What's our scale factor for response spectrum, right? 1.5, that's the importance occupancy category. R is equal to 1.8. If you were doing a special moment frame, that R would be equal to 8. That's a fraction of the force, right? We are approaching something closer to the actual force, earthquake force. The system damping is 0.15. That means collaboratively with the isolators and the building, we want a damping of 0.15, ideally. Mass source for our seismic, obviously, is the self-weight of the building. So we're not talking about winners yet, but we will get to that to see who is the worst of the two evils. This is just standard gravity loads, dead load, live load. That's just input for the model. Right, this is the interesting part. What's our design preferences? We are not using a special moment frame. We are using a frame on base isolators. What does that mean? We can drop it to seismic category A, not D, right? That means we don't have to do the terrible checks of strong column, weak beam, which also would make your column pretty big, not good for your carbon footprint. Your seismic detailing, you don't have to have links, the space of the size of your 2 fingers, where a client is going to say, I've never seen that before, you're over-designing. Normal thing, as we all know. We made a little judgment call with the cracking, right, for deflection. If you're doing a normal moment frame, I think it's 0.7 for columns, 0.5 for beams. We said, let's crack the column stiffness a little bit, 0.9, and the beam stiffness, 0.6. Okay, around there, right? We put that in. Right, and Professor, please, anytime you want, you're the
Yes, well. Go ahead.
over-the-top scientist, right?
Calm down.
Right, this is the fun part of the results now. We got 2 modes, 2 molar responses. Each one was over 2 seconds with a mass contribution of, is that one 96%? That's excellent, that's what we're looking for. If you remember what I told you about the peak, right? We're down that slope right now with a period of 2, which means we're out of resonance with those accelerations. Am I saying that? Yes, yes, right, I know. And we're getting most of the mass. We don't need to add all the masses from various modes, right? Second mode now moves in the other direction. Again, 2-second period. It was at 99%. What? A good, okay. That's most of the mass is participating in this earthquake. So that's great. Right? So what we define effectively is what those modes mean is, let's say the up and down direction, it's moving in that direction without twist, without translation, and at 2-second period with 90-something% mass. And in the other direction is moving that way. There's a little twist on this diagram, but the scale was off. So
Yeah,
ignore
the scale
that.
is off.
The scale is off. Right. Right. Now, early in the presentation, we were talking about the isolators had a stiffness of 550 kilonewtons per meter. What does that mean? Right? We got a displacement of 178 at the isolator or ground floor level. I'll show you eventually that we actually do get about 100 kilonewtons lateral load from the seismic behavior. So it's making sense. 100 over 500, 20% of a meter. It's kind of adding up. The blue and the red are the two orthogonal directions. Right. What do I have over there, boy?
That's not the story forces.
That's the story forces there. Right, and you can see, right, that you have about 500 kilonewtons per story acting. So that's just a summary, 500 kilonewtons. When we did a pin base check relative to this isolator, we got 3 times the level of the force. So we're showing you already the isolators are working, right? The building is not feeling the full brunt of a traditional building. So let's see what the reinforcement design looks like. This is ground floor. Let's go to the junction in the middle, which should have the highest moment or whatever. You have 1,022 millimeters squared for your 450 deep beam. Not bad. Everywhere else, 750 something, 703. This is ground floor. Looking reasonable. Reduce carbon footprint, less material. Let's go. Next slide. Columns are just minimum reinforcement. 2,500 millimeters squared. I think it's, what do we have there, Luigi? 12 or 16 T18s there. But it's minimum. All right. So let's talk about the wind. We know what the lateral force on the building is. 500 kilonewtons, lateral load at the base. Isolator about 100 kilonewtons. Go back one there, Luigi, sorry. We have already implemented, because the data is available under the guidance of Mr. Gibbs, right? And we implemented our climate change factor from the PAHO Peter Vickery maps, I think it is. No. Yes, I think that's it, right? For wind speed of 182, that includes the 10%. So we're going with 110% 3-second gusts. Wind calculations, we get about 300, 330 kilonewtons per story. All right, there's the calculations that the program does. So just one flip back there. So, no, you can stay there. Yeah, go back, sorry, ahead. So that's who is the worst? At this point, earthquake governs the design over hurricanes, at this point. But we'll talk about that a little bit later because we can even reduce it more. The lateral load, 65 kilonewtons at the base. So it's below the isolators. You go back, right, the reinforcement, almost minimum. 880 kilonewtons over the junction, 500 just minimum everywhere else. On your beams, that you should see what floors those are, first and second floor or something. Right, so the reinforcement details at ground level, you have, what we have there, 2 T20s and 1 T16 at the bottom. That's the highest. Everywhere else, first floor, I think it's 3 T16s, 3 T16s, general spacing of shear links. Very almost gravity design type reinforcement on these isolators. We have a little thick head there because you have your shear to deal with. Second floor, it just reduces. 3 T16s going to minimum. This is across the section of the short section of the building. Right, you can skip that now? Yeah, same thing. Ooh, okay?
Yes, yeah.
Right.
I think now, what should we do?
Right, we had some images and more technical information and a summary. Luigi?
Yes.
You could bat?
I don't know, it's up to you. Want to change?
Yes.
Okay. So, thanks, Riyad. Well done. what I'm going to do now is to provide the other way around, the conceptual design. Why, for example, base isolation can motivate and can be a good choice for this design. And there are a few slides that I left at the end so that we can then leave with these messages, which are very important. Yeah. Okay. Yes, it's there. Oh, it is there. Yes. Okay. So basically, there are multiple ways of dealing with the design. It could be strength-based and ductility-based, which is the ordinary design that relies on a Q factor or R factor in ASCE, where we look at, for example, relying on ductility on plastic rotation, interstory displacement. Hence, we comply with the life safety and collapse prevention limit states in an ordinary manner. Right. Yes, then stiffness is very important because we want to ensure the damageability limit states. Then there is strength. Next. And what is also very important when we look at the stiffness, and I'm going to show you in a case that was recorded after a major event, is that we need to control, primarily for hospital buildings, like the one that we have just shown, the operational limit states. And the operational limit states can prevent the use of facilities. Shalini just showed that, for example, you can see a building standing, but all the interiors have been collapsed. And in fact, this is the case of a number of hospitals where acceleration have been attracted. Because the stiffer is the building, the more acceleration will attract. Hence, you will have tilting and overturning of a number of components. But also displacement is important, because then you want to prevent all the non-structural features to be damaged. At the end of the day, the conceptual design, in any design actually, and more specifically with this type of a system, should be a trade-off between all these four components that are strength, stiffness, ductility, primarily related to structure, but also in terms of response parameter, acceleration, which generally is something new for engineers, but it's something very important for the functionality of components. You go, please, next. Now, what is the example that can convince not me, but I guess most of us, that this system is working? And more importantly, we can have evidence of the performance of the structure. This is the Olive Hospital in that was affected heavily. In fact, it collapsed during the 1971 San Fernando earthquake. You see that there was a spread of damage all around the system, and in fact, it had to be replaced. So this was 1971 when I was born. Go next. Now, what has happened after a number of years? 1994. So we are now looking at the performance of a new building that has replaced the previous one. And in fact, this system now does not rely on the frame type of system that we have seen before, but it employs a number of shear walls. So there has been a number of years in between 1971 and 1994. The technology has changed and the system was replaced by a more stiffer one. So is it safe? What will be your answer and your guess on this? Not safe enough. Let's see what this enough means, though. And I will show this with instrumentation. So I'm not going to convince. We'll look at it and we'll see how the system performs. And luckily, during this earthquake that we are all aware of, there were a number of instruments for this Olive Hospital. You see all these traces here that are the recording as collected during the earthquake by structural health monitoring that was along the height. So we had the possibility to follow how the building was filtering the earthquake as it was recorded. So the base one, can you go to the next one, please? Okay, so this was 0.8 at base, and it became 1.53 at the top, which means that there was an amplification of 2 moving from the base up to the top, which is something that is affecting highly the structure, because it means that you have more than nearly double of the acceleration of gravity at the top. And all the systems are exhibiting a low resistance with respect to this large force. But more importantly, if we look inside, so the system was structurally safe. So that's very important to note. But go inside the building, next one. And what has happened is that, okay, just to show you that we moved from the first example here, that was the 1971 building, to this one here, we have now more stiff structure, but because we are moving leftwards on the spectrum, we are attracting more forces. And what has happened internally? Let's show this. I think is the next one. There were a number of components that are sensitive to acceleration. And because the acceleration was increased because of the larger stiffness of the system, all of them, I think it's the next one, failed. Okay, it's not here. But this graph is showing, though, another important aspect. Let's look at this. So the previous one, can you go to the next one? I think there is one showing the damage. No, next, after this. Or we missed that one, no? Go ahead. Okay, no, forget. Let's go back. So I can provide you that one. It's an interior view of what has happened in terms of collapse. Most of the component failed. Now, what is this graph showing? This is taken from Professor Miranda from Stanford, and he has performed a very thorough study collecting the cost breakdown for most of the buildings that form part of our built environment. And they've been classified according to offices, hotels, and hospitals. Okay? And this graph is very simple, but I think it's very attractive for decision makers in this sense. Firstly, let's consider offices. There are 3 aspects to be considered here, and this is connected to what I just mentioned. Why? Structural elements. For this type of system, the cost is roughly 20%. The remaining part is 62%, and this remaining part is non-structural element. And we have also the interiors that here counts for nearly 20%. Now, without going through hotels, let's move to the hospital that we are more interested in. So what is happening here? We have squeezed the cost, generally 10% roughly, of the overall structure. And then when it comes to the remaining part, it is the breakdown shows that there is an equal the distribution between non-structural component and structural component. What does this mean? So if we go back to the previous building, with the failure that has happened, we have lost nearly 90% of the overall cost of the structure, while the structure that counts only for 10% can be saved. So as Tony said, not safe enough. Actually, I would say it was not safe at all, because we have lost most of the money. And more importantly, what we have lost is this part, which is functionality. And that is why we are interested, as Riyad has shown, please go to the next slides, to move on the full operational, even for rare event, which is the performance-based metrics that we should get. Next one. Where, these are the examples of part of the damage that was collected in that building. So you see that all the cupboard, all the cabinets that were inside the building could not be used. And this is something that we have seen a number of post-earthquake events. For example, a number of electrical, mechanical components failed, ceilings were damaged, lighting were highly affected. So all this performance level cannot be achieved with ordinary design. That is why, please move to the next one, these are also part of the leakage that took place in a number of these, of the piping that was present. Next. How we should then design how should design the critical facility? Next one. There are 2 options, and these are the typical way of design structures. The typical design is based on conventional approach, where you generally look at elastic behavior, which is something that could be over-conservative, not economically affordable, or you can rely, as we mentioned before, it's not very clear here, it says inelastic behavior, i.e. it means that we accept damage. This is something very clear to structural engineer, but to other people it's not clear, even to architects. I think you are 2 of this today, you've grown. We design for acceptable damage. This is based on R factor that Riyad was showing before. So it is based on ductility. Ductility is a word, now going to 1 million words, we added a new one today, but it means that we see damage when we go on after an earthquake. We don't see, ductility. We see the bars that have been yielded, we see the concrete that has been heavily damaged like this. Do we have an alternative? The alternative is yes. This one is innovative. If you look at the application, probably it's not as innovative as it should be, but for sure it's not conventional, it's not traditional. What we do in this type of approach, alternative approach, we look at vibration control. And by vibration control, we mean everything that can limit the unexpected or the excessive vibration that the building can have. This is an application of a retrofit of building in Italy for a school. This is the civil protection in this was near Rome, and it was built on a number of isolators. Why? Because these are the critical facility that one want to preserve so that they will be operational, like hospital, soon after a major event. Go to the next one, which I think is the last. No, this is yours.
Oh, right. Okay. Something runs there. All right. Summary based on what we discussed today. It's kind of linked to the discussions and presenters, at least yesterday, right? Criff is not here, Umar? Okay, reduced insurance costs to Criff, right? Inherently flood resistant due to a high ground floor. It's already jacked up, Professor. Right, so, out of the box thinking, simplify design and construction.
It's yours.
See what's happening here. Climate resilient. It's designed for the maximum considered earthquake. It's designed for the maximum hurricane. Volcanoes, we'll have to discuss another time. Right? Cost effective. I mean, you could see the members, the reinforcement, the superstructure came down significantly. Where's Shalini? I'm calling this a smart building because it knows how to dance with the earthquake and resist the hurricane. Sorry, it should be smartest building, apologies. Freedom of architectural design, because we're not guided by seismic design category D and all these frames and pre-qualified connections and detailing and these kind of strong column, which the architects hate, obviously, because of the size they are. So I think in summary, that's it there. It's a smart and safe facility during and after disastrous event, which remains operational, resilient. Oh, we were trying to talk about resilience in a word. I think we were trying to say that's our definition. All right, just some other notes. Right, thank you, everyone. So I hope you all go away thinking that base isolation is something we should really be looking at doing, implementing, and improving in the Caribbean.
Thank you. Just one last word, because the other thing was a bit quick on the cost, which is always left at the end of any list for engineers. If you go back there, there is an acronym that, again, architects are probably more familiar than us, which is LCA. And this is very important when you look at the cost. Don't please only pay attention to the capital cost, because for this type of solution, you have to look at the overall cost. It may be 10, 15% more at the beginning, but then you do not need to evacuate the building. You don't need to do any extra work after a major event. So this will offset tremendously the cost, not only for operations, but because you do not need to intervene on structural, non-structural, and even contents. So the cost will be much, much cheaper than the ordinary building. Thank you.
Gentlemen, thank you for that entertaining presentation.